My name is Andrew Whittaker, and I'm a SUNY Distinguished Professor at the University at Buffalo and a former Director of the Structural Engineering and Earthquake Simulation Laboratory that is more widely known by its acronym CSEESL. CSEESL is an internationally recognised university laboratory and was home to one of the first earthquake simulators in the United States. Although its reputation was built around developments in structural and earthquake engineering, the laboratory now includes facilities for geotechnical, wind, fire, and materials engineering research. The laboratory was constructed at the time of the building of Ketter Hall. In the early 2000s, the laboratory was expanded with grants from the National Science Foundation and support from the state of New York. This addition to the Ketter Hall building served as the largest node in the NCEEER Collaboratory, an NSF-funded, geographically distributed family of earthquake engineering laboratories, from 2004 to 2014. CSEESL was home to significant advancements in structural and earthquake engineering. Another feature of the laboratory's history is a 25-year engagement with industry partners, with a focus on equipment qualification for mission-critical structures. Seismic protective devices and systems are designed, detailed and tested to protect framing systems and equipment from the effects of earthquake shaking. Examples include sliding and elastomeric bearings or seismic isolators, and fluid viscous and viscoelastic dampers, and yielding metal braces. Much of the development work in the past 25 years, which backstopped the mandatory language and commentary in US codes and standards such as American Society of Civil Engineers, ASCE 7, ASCE 4, ASCE 43, and the AASHTO Guide Specification for Seismic Isolation Design, was executed in Ketter Hall. Experiments conducted in parallel with theoretical, numerical, and code developments have sped the transfer of technology from UB into design practice in the United States and abroad. We have worked and to continue to work closely with industry partners on technology development, including Taylor Devices in nearby North Tonawanda and earthquake protection systems in Vallejo, California. We greatly value these industry connections. A number of faculty in the department have contributed to the development of seismic protective systems. Key contributors are Michael Constantinou, Andre Reinhorn, Larry Sung, and George Lee. Now let's hear about work, past and present, from a number of my colleagues.
Hello, my name is Michel Bruno. I am a professor of structural engineering. As part of a team with Professors Reinhorn, Constantinou, and Tivanayagam, I was the principal investigator for the $20 million award we received from the National Science Foundation and the State University of New York Construction Fund. Now that grant made it possible to build two relocatable shake tables, a 63-foot long, 30-foot tall reaction wall, and a 3,200 square foot strong floor, all of which are those housed in the new 14,000 square foot addition to Ketter Hall, where most of our large-scale experiments have been conducted since 2004. Now, the goal at the time was to create what was to be the world's most versatile earthquake engineering facility. Thanks to this versatility, as one of the many users of the facility, I have been able to conduct many fruitful experiments to investigate, among other things, the seismic performance of steel structures. We have also conducted some very exciting research to investigate the cyclic and elastic behavior of composite wall systems to make it possible to use these walls in seismic regions. Now, these walls are essentially built as a sandwich systems with steel plates on the outside and concrete in between. That structural system has many appealing advantages, one of which is particularly important, is speed of construction, because it positions the system to be a game changer in the high-rise construction industry. In fact, this system is also sometimes referred to as the speed core system for that reason. Now, in our labs, we've used a special test setup to apply to the walls a gravity load of approximately 1 million pounds before applying lateral cyclic loading to the walls until their failure in flexure. Now we tested C-shaped and T-shaped cross-section walls, and they all behaved in a ductile manner, which validated our proposed design methods. So the experiment conducted was critical because it was part of an extensive research endeavor that led to the addition of this structural system in building design and code standards, which by itself is needed to allow for their construction in seismic regions. And there has been much more work that we've done in the lab, as you will hopefully discover going through the publications that we have produced as a result of all of this work. But in summary, I'd like to say that the knowledge on how to design and detail steel structures to achieve ductile behavior is vital. It's essential to ensure that their satisfactory performance will be achieved when exposed to many different types of extreme events, such as earthquakes, but also blasts, collisions, and other conditions that push the structures into their inelastic response. Now, it is great that the experimental work performed in our lab has helped generate this knowledge, and in turn has been instrumental in getting a lot of innovative steel structural systems adopted in design codes and standards, such as, for example, the American Institute of Steel Construction seismic provisions for structural steel buildings. This has made those systems readily usable by structural engineers in their everyday projects.
My name is Pinar Okamus. I'm an associate professor. The overarching goal of my research is to enhance serviceability and resilience of building and bridge structures through the use of better materials and structural systems. Shear walls are commonly used in building structures as a lateral load resisting system. However, buildings built before the implementation of the modern seismic design codes are prone to damage and may need retrofitting. Traditionally, retrofitting it is done by stiffening a structure. In our project, funded by the National Science Foundation, we took a different approach and intentionally made our walls softer to reduce demand on the structure. In addition, our retrofit method involves turning traditional walls into walls that can rock over the foundation and bring the structure back to plumb position. These rocking walls are known to have much less damage during a major earthquake than traditional walls. We hope that this will enable engineers to achieve resiliency through limited damage and rapid occupation of buildings after an extreme event.
My name is Andreas Stavridis, and I'm an associate professor. My research focuses on the assessment and improvement of the structural performance of buildings and bridges under ordinary and extreme loads. To achieve that, my research group combines numerical models and physical tests of large-scale structures. For this type of research, having access to a laboratory such as the one we have in Ketterhall is critical. So recently, for example, we concluded the test of 3 60-feet-long beams that were extracted from an actual bridge on Audubon Parkway. These tests were part of a project that was funded by the Department of Transportation and aims at extending the service life of deteriorated bridges by rehabilitating them with fiber-reinforced polymers. Extending the service life of these bridges by even 10 or 15 years can have a significant impact on the safety of the users, but also on the budget of the bridge owners. There are not many labs around the country that accommodate these testing requirements. So for another project, for instance, that is currently ongoing, in a few months we will be testing unreinforced masonry buildings under seismic loads. The project, which is funded by the National Institute of Standards Technology, that's NIST, is investigating the effectiveness of strengthening methods that were applied on these buildings in California over the last 40 years. These methods were never tested with three-dimensional shaketable tests, such as the ones we plan to conduct on 2 buildings that were actually constructed on the table and will test to failure in our lab. And again, there may be, at the best, one more lab in the country that can accommodate these tests. So our lab can test large structures under service and extreme loads, as well as wind and thermal loads in the wind tunnel and the furnace. Yes, it is very well known around the world. However, we realized recently that our undergraduate students spend 4 years in our department, and unless they personally take some initiative, they don't get to spend time in the lab. We needed to change that, and so we designed a project for the class I teach on reinforced concrete design, for which the students design, construct, and test to failure beams of real size. So I'm really hoping that in the post-COVID world, we will be able to take the students back in the laboratory and do these projects for years to come.
Hi, my name is Anthony Tessari. I'm an assistant professor. The response of infrastructure, for example, tall buildings, to extreme events is influenced by the interaction between highly variable, naturally occurring soils and engineered elements which form the foundation and superstructure. Current codes of practice for design largely ignore these interactions, regarding them as conservative measures. However, these may be detrimental and even crucial in the context of critical infrastructure. Our recent experiments support this proposition and emphasize the need for advancing fundamental understanding of the interaction mechanics that can be represented in predictive mathematical models, validated through controlled experiments, and incorporated in design. We have coupled physical models of the soil foundation system with virtual computer models of the superstructure to zoom in on the soil foundation interface. Through this approach, called hybrid simulation, we simulated differing soil foundation interfaces representative of extreme event conditions. This is impossible in any other form of laboratory testing. The combination of a 20-foot tall laminar box holding 150 tons of soil, earthquake simulators, and distributed control systems that enable this research is unique to UB. The results of this research is being used to improve resilience in design, enhance risk-informed decision-making frameworks, all of which will lead to safer and more economic design of buildings in the future.